Hello, my name is Alexey Grishchenko, and today I will tell you about the modern data architecture. First of all, I will tell a bit about me. I'm an enterprise architect working with Pivotal. I got a big amount of experience with data processing system. I'm working for more than 4 years with Hadoop, 5 years with MPP databases. I am an Apache Spark contributor, and I'm blogging about it in my personal blog. You can visit it and read many interesting information about the distributed systems. First of all, the history of this talk, how it happened, how it occurred. Something like half a year ago, one of my colleagues came to me and said that they got a problem with their customer. Their customer has a traditional data warehouse solution. They got a number of problems like disaster recovery side, like implementing the big data approaches, and they are completely lost. They don't know how to do it and how to apply it. They heard a number of buzzwords like data lake, like Lambda architecture, but applying it to their platform is very, very complex, and they don't understand how to proceed after this. So I decided to make it, and I made a general presentation of different approaches. But after the time, I understood that if you will show just what is a data lake, what is a Lambda architecture, it's not enough for the people to understand how they can transition their system to this state. It's enough for many people to implement the system from scratch, but implementing from scratch is not a good option for a big enterprise. And in this presentation, I show how you can transition from one architecture to another and how your system will evolve over the time. So everything starts with the front end. How this talk happens and how these slides occur. Half a year ago, one of my colleagues came to me and said that, we got a customer and they got a traditional data warehouse system, and the problem is that they don't understand how to move forward. They got a number of problems, and they heard a number of buzzwords like data lake, Lambda architecture, and they just cannot imagine how it fits into their platform and how this can be done after all, because without redesigning and re-implementing everything from scratch. So how it works in general. And this is what I will tell you today, and let's start. So how everything started, how all the data processing system started. First of all, it was just a simple application running on a single machine, and some people accessing this application from their laptops. Then backend appeared, so it was just a set of services, and services stored their states in some kind of a persistent store in the database management system. So this is how many applications work even today, but it was just the beginning of the era. All of this worked on a single machine. But what about some business intelligence, and in general, what about analytics? How users can analyze the data in this system. So we just put it there and put a BI layer on top of the database management system. So in general, the data flow looks like this. The problem for most of the people developing applications is that they are focusing only on the front end, or they're focusing only on the back end, they're writing services, and don't see the whole picture of the enterprise, how the data comes to the system, how it is transformed, how it is consumed by the end users. And this is the problem for many enterprises. This is why they cannot understand how to move forward. So, of course, was it fast? Yes, it was kind of fast, because the amount of users was very small. The latencies were small once again. So time to insight might take 1 or 2 minutes, because the data arrives to your database, you just build some kind of report, you restart it, and it gives you a result. And yes, everything was running in the beginning on a single server, because the workload was very small, and the servers were very expensive. So buying a number of servers for an enterprise was not a good option. So then the situation has changed. More and more users get their workstations, and the workload on the system increased. What happened? We got more users, and the latencies became a bit better, a bit worse, but it wasn't a big problem, because for user wait for less than a second for executing some action is not an issue. But we decided to split it, and after this time, front-end and services usually run on a separate hardware from the database management system, or at least on a separate virtual machine running on the same hardware. It depends on the enterprise. What if we have even more users? Because the amount of users grow, we got some external users connecting through the internet to our applications, and the problem increase. So we split it again, and we got a number of front-end servers, and of course some load balancer in front of them. But the idea is that we got many of them. But what happens next? As you might understand, something like 15 years ago, 20 years ago, automated systems come into the picture, like automated banking systems, like automated system for telecom. When you make a call, this call is getting to the billing automatically, and from the billing it gets into some kind of different solution. So we got a number of systems, and thousands or millions of people started to connect to this system. And what happens with the database? How do you think? So something like this. So you get only a single database, and all the system depend on this. There might be a number of instances inside of it, but it's still not able to survive. So what we can do with this database? First, we put all the BI out, because it's not very important. We need our transactional systems to live. And then split. Yes, we split again. Eventually, it will help us. And we got this kind of system. For each separate system, we got separate database on a separate platform for automated banking system, separate database for CRM, separate database for ERP system, separate database for accounting. So for everything, we got a separate databases. And BI solution just looks at them, and the problem that latency grew very, very much. So now, time to insight is something like 35-40 minutes. So we can remove the platforms, because we know that everything works on a separate platform. Even front-end and back-end can be separated in this way, and a number of databases. And then we start to build reports. First user tells that sales went up 10%. That's great. Another user built report on another database that has almost the same data, like CRM system and the billing system. On the billing, it tells 10% up. On a different system, it tells 20% down. And there comes another user. One moment. Yeah. Another user that tells you stop loading my database with your reports. Because you know the problem of this is the problem of OLTP systems versus OLAP systems. When you get a transactional system like a billing, it is optimized to work in a single small transactions. It's something like just Oracle database or Postgres or something like this. Small operations getting written, getting right. The best platform for this is a single big server with a shared storage. Shared storage has some SSD drives, has tiering, and so on. So it works very fast. But when you start to run select on all the calls for the last half a year, it needs to bring up all this data. It invalidates the cache that is maintained on the network attached storage level. And the problem is that all the OLTP workload, all the important workload, is getting very, very slow. And at this moment, not developers, but the people responsible for this platform start to kill analytical queries, saying, don't go here at this time, don't go here at this time, don't run these complex queries on this platform. You should validate your query before running, you should give us a query, we need to validate that it will eventually run, and only then we will allow you to do this. And many problems occur. So, in general, this stage was the beginning of the era of data warehousing. When you get a number of source databases, you extract data, transform, and load it to a different database that is called data warehouse. And on top of this, you store your BI reports. The main problem is that latency has increased for up to 2 days. So nightly, the extraction process runs, and it collects all the data into the data warehouse. And then it goes to the BI. The problem was that users did not stop with a single small BI system. They need more different systems, like OLAP, it's online analytical processing. In general, it's I'm referring to the OLAP cubes. You know, the system when you pre-aggregate the data for large tables to be able to deliver the reports faster, and some data mining applications. What happened then? Said that we need a secondary site, because if something happens with all of this system, then we're completely out. What should we do? We should add the secondary side. Of course, secondary side is more important for the OLTP systems because they are business critical. If your billing has failed, then everything has failed, and you cannot process the cannot serve your customers, your end users. But if the data warehouse has failed, it's not a very big problem. Your analysts will not get some data, some insights. But again, sometimes pass, and the disaster happens. The system switched successfully to the secondary side, but there is no data warehouse. And this is the first question. So what happened? Why cannot we access the data? And business understands that there are 100 or maybe a couple of hundred of people that cannot do their work because they don't have a data warehouse. And this is because of disaster. And it will take some time to bring up a data warehouse on this specific platform. And this time is quite big. It might be a couple of weeks or even a month. So what happened after this? They decided to do a disaster recovery for the data warehouse. Data warehouse is very big. ETL is usually developing in a random way. So we need to extract this data, okay, we develop a script to extract this. We need to extract this data, okay, develop a script, extract this data. There is no really a way to sync these two platforms in the real time. You cannot use approaches specific for Oracle database or Postgres database with replication, because the amount of data written to this platform is this big, it is batch loading. So we got systems loading 4 terabytes a day. If all the 4 terabytes will go through the write-ahead log, replicate it and replay it on the target platform, it just don't work. It's not working. And it's not the way to do it. So the only option here is to do a backup restore. Making a backup can be done only in the maintenance window, because backup reads all the data from, or at least big part of the data from your data warehouse. It loads the hardware. It should be done where no reports are running on the database and no data is loaded into the database. It's written to some kind of a shared storage, and then it is loaded to the secondary side. And again, we got a problem. Why our data is so old? This is the question for the first platform and the second platform. Because the more data you have, the greater latency. So your data warehouse platform should be very, very big and fast to be able to process all the data from the source systems. And usually it's not so. So many platforms, many business user developers decide not to load data daily, but load data bi-daily or load data weekly. And it happens that for business users it's not always sufficient. So then we are at the point we got now. So now most of the customers got this specific situation. Some of them don't have disaster recovery side. Some of them stop at the backup, not doing the disaster recovery side, just have a backup on a separate platform to be able to restore. And this is a very big problem of latency that cannot be solved, and the amount of sources of the data, because they are increasing. So we need to invent a bicycle to improve this platform. First of all, what we should do is to replace ETL with ELT idea. So instead of transforming the data on the loading, we are doing load one-to-one. Why? We had ETL after all. The idea was that data warehouse was the same database, same Oracle. And if you want to load all the data from all the source system, the amounts of data are huge, and you just cannot store everything. So people decided that if we got a table in a source system with 50 fields, and we need only 5 of them, we will load only 5. We will not load the whole table. And then they decided that if we need data only about our corporate customers, not the individual ones, we will load only this data, so the subset of the data. This is what's called extract, transform, load, or ETL. So we extract data, transform it on the flight, and then load. We need to go for ELT to store the same copy of the data. We can do it because there was a shift in the data warehousing paradigm something like 15 years ago or 10 years ago, when massively parallel data warehouses were introduced, massively parallel database management systems. First of them were Teradata, then we got a number of different ones like Oracle Exadata, Netezza, Greenplum, Vertica. So you might have heard any of these names. So, we got ELT, but it does not solve our problem really. What can be used to solve our problem is change data capture. It is called CDC. The idea is that you got a transactional system, source transactional system. This system has a log of all the operations happened, all the edits, all the updates, inserts, deletes happened in this database. You just parse this log and copy all of these commands to a separate platform and reapply them. This is the idea to decrease the latency, because instead of extracting data daily, you're extracting data each hour or each 5 minutes. We got a number of people doing this with latencies of 30 seconds, 1 minute, 5 minutes. But what kind of problem we see here? The problem is that you cannot enable CDC for all the platforms. Because initially, what will mean if you enable CDC for all of them? It will mean that your single database, single data warehouse, need to replay in real time all the transactional operations happening on all the source databases running on separate hardware. And the data warehouse in database is not a transactional database. It's developed for handling analytical workload, huge scans, not single row inserts. And it happened that you just cannot enable CDC for all of them. You will enable it for only some small part of the databases that are the most critical ones. This way you can increase latency, but you decrease latency, but you will decrease it only for some small subset of the reports. And again, why our secondary site is so old, why our data in the data warehouse is so old. So we need to move forward and get a next architecture. And now we get our problems. Time to action takes up to 7 days. So if you are switching to the secondary site, you might see the latency of 7 days. So event happened in a billing. Then when it comes to the database and business users can build their reports on this, 7 days are passing. Next is amount of data is growing. So you got many source system and the amount is increasing. At the moment, everyone talks about extracting the data from external sources like Twitter, Facebook, and so on. And if you get this data, you get even bigger amounts of data. And if you cannot handle in the real time or in near real time fashion all the data you have now, what will happen if you will have more data sources and more data? Okay, and then MPP storage is really expensive. So when you got an MPP platform like Teradata, like Oracle Exadata, you know that increasing this platform is possible. It promises to scale linearly, but the price of this storage, price of this extension is very high, and they are all proprietary. So the second platform, two problems can be solved with data lake, and one of them can be solved with Lambda architecture. And now I will tell you what it is, how it works, and why do we need it at all. So, data lake, how it looks like. Data lake has two main pillars and two main ideas. First idea of the data lake is offloading the data from data warehouse to Hadoop cluster, because the biggest amount of data you usually store in your data warehouse are the copies of the source system. If you will move all these copies to the Hadoop and retarget your ELT to Hadoop cluster and port some of the data processing tasks to run on top of Hadoop, then data warehousing platform will host only aggregates. For instance, if you know what happens at Facebook, Facebook has 300 petabytes of data stored in different Hadoop clusters. And they run mainly Hive on top of this. But they got Vertica as a data warehouse solution. When they build aggregates inside of their Hadoop clusters, they load this data to Vertica. In Vertica, they got BI solutions that are analyzing data out of Vertica. They don't give end users, don't give business analysts access to the Hadoop cluster, because Hadoop is complex and they can easily break things by generating Cartesian product and so on, and no one can prevent them from doing this. This is why this is the first pillar of the data lake. The second one is increasing the amount of source systems and loading so-called unstructured data. I don't like the term unstructured because all the data has structure, but this data is mostly JSONs, XMLs, and different extraction from the source system. It might be HTML. The idea is that you cannot just load this data to the data warehouse. If you will load it into your MPP platform, of course you can load it in a string and it will be stored in a table in a single field, but it is very inefficient way to do this, and you will have many complexities in parsing and analyzing this data. This is why the best place for this data is usually your Hadoop cluster. So these are two main pillars of the data lake, how it works and why you, after all, need the data lake. There are many differentiations. It might be not called data lake, but data hub. Cloudera prefers this term, but the general idea is exactly the same, that you need Hadoop cluster to offload some of the data warehouse workload. And usually you offload the biggest part of the data, which is detailed data copied from the source system. For instance, we got a telecom that loads 4 terabytes of the data daily, and they load this data to Hadoop. Then they aggregate the data and load this data to MPP database for the BI and analysis and so on. The idea is that these huge amounts of data, it's something like 300, 400 terabytes or close to petabyte of data, they store it only in Hadoop. Data warehouse platform has access only to the aggregated data. In general, from the data warehouse, you can query the data line on Hadoop. At the moment, most of the database management systems allows you to access the data in Hadoop. You can do it in Oracle, in Greenplum, in the same Teradata, in Exadata. You got connectors to load data from Hadoop. Some of them are more efficient, some of them are less efficient, but after all, you can do it. So here is how our data lake will look like. This is the source system. When we add data lake, we got this architecture. There are a number of problems. First of all, how you will replicate Hadoop cluster. This is the main question for most of the customers implementing Hadoop. We want first site, we want to have a secondary site. How we will replicate the data from first site to the secondary site. And I will answer this question shortly. There are a number of options in replicating the data, but not all of them are ideal. First, we need to understand that here we decreased the workload on the data warehouse, we introduced Hadoop, we allowed to introduce additional source systems to so-called unstructured data processing, but now we still have almost the same latency, and we got the problem with the secondary side of Hadoop. Next thing to do is Lambda architecture. Lambda architecture is getting popular for the last year and a half, I think. And the general idea of Lambda architecture is the following. You got some kind of a source system. This source system feeds two separate systems. One of them is real-time, that calculates some data, maybe in memory, but the general idea is not really for this system to be in memory. The idea is for this system to be real-time. So process the data, incoming data, as a stream of events. The second source is the batch layer. In a batch layer, you store the master data set. The idea of master data set that you are not transforming the data as you load it. You load the same data that happened, the same events that happened. After this, you transform it with batch views and feed it to the queries, to the BI system, and so on. The idea is that if you have lost your speed layer, you still have all the events in your batch layer, you can replay them. If you have some problems with the data processing logic in real-time layer or serving layer, you still have a master data set. On top of this master data set, you can regenerate your batch views and change the bug. For instance, what usually happens in data warehousing platforms. You got the data, if you got ELT, you are lucky. Your data is extracted as an exact copy from the source system. But what happens next? Next, you got the difference of the data that was loaded, like new 1000 records. You transform them and load to the next table. It loads to the next table and so on. Sometimes data warehouses has 5 layers or 6 layers when the data is loaded from one to another. The problem is that if you got a bug in one step in the first layers, you get to reload many tables on the next layers. And if you don't do ELT but do ETL, and you got a bug in ETL code, you have to re-extract huge amounts of data. And it's not always possible. The idea of data warehouse initially was that you got a transactional system, for instance, billing. In the billing itself, you store only last 2 months of events. In data warehouse, you store last 5 years. You don't need more than 2 months in the billing. The billing can be much, much smaller. You don't need them. No, maybe for before the billing you might need 3 last months for quarterly calculation of the services consumption. So that's it. Now we got Lambda architecture and how it will fit into this whole picture. Where do we have a real-time data stream? The only place where we got it is CDC. Change data capture gives us a stream of events from the source databases. So the logical idea of how this can be done, we just put our in-memory data store or fast in-memory layer to the CDC. And CDC serves the data to the Hadoop cluster and to the real-time system. And then BI asks both Hadoop and the real-time system and maybe even the data warehouse. But we still got many problems with this architecture. It does not solve the main issues with the previous one. Yes, it might increase latency up to 0. For some of the systems you might have something like 2 minutes, 3 minutes delay. So user made a call, in 2 minutes you see this call in your report. For some of the users it's very important. But you know, the problem is that when you show the business user the first report that shows these statistics in real time, users understand that this is possible, and after this they try to ask all the reports to become these real-time reports. And you just cannot do it because it's very complex. You cannot do CDC from all the platforms. It will be just an amazing solution. And the last step is our problems. Again, too many standby systems. So if you will take a look, we got standby OLTP databases, we got a standby data warehouse, and how do you think we can enable the in-memory store if this the disaster recovery site will be activated? Our in-memory database on disaster recovery site will be just empty. So it's a big problem. Then, how to replicate the Hadoop cluster? I already told you, but now I can tell you a number of options for replicating the Hadoop cluster. First of all, it is dual ETL, so you load data to both clusters at the same time. You have to implement it manually, it's a complex task. Second is using proprietary solutions for replication. It's usually not recommended because proprietary closed source solution on top of the Hadoop cluster is not the thing you would like to run. And the last option is the one I will show you now. How to sync data in real-time systems between a number of different systems. Like you got real-time cluster in the production system, in disaster recovery you don't have it. How you can do it? And how to better sync data warehouse. So making a backup, copy this backup to the secondary site and making a restore will take you 3 days. Of course, it depends on the amount of data. For some small data warehouses, it may be done within a number of hours, but in general, data warehouses are starting from 10 terabytes, 15 terabytes, and for 15 terabytes, it will already take you at least a couple of days. So the answer is pipelining, or as I called it, streaming. How it works? So you got a front end. So user communicates with the front end, then front end goes to the back end. For the database writes some data to the log. In log, you copy data for parsing it in CDC. You go with the ETL that extract data into batches and load this to the data warehouse. And then from the data warehouse, you got a source layer, which is just a replica of the database in OLTP. Then you got detailed layer, some transformations happened. Then you got some data marts built for the business users. And they connect to this solution. This is how, in general, your pipe looks like. What can we do here? First of all, we can introduce the reactive programming approach with the queues. And this queue might be external queue, not internal, but as a separate solution. This way, we can solve a number of problems. First of all, we can get the data from the queue and not go into the OLTP database. We can just get the information that comes to the database before it really happens and process this information on the flight. And the last one, we can extract this information and put it into the Hadoop cluster at the same time. We can extract this information and put it in real-time in-memory cluster. and we can extract this information and replicate it to the remote side. This is the general idea of pipelining. You're writing data once, and when this data is written, you can replicate it to all the other sources, all the other systems at the same time. So here is the source picture of what I propose to do, and here is how it looks like with pipelining. So you get a number of queues. You get a separate queue for replication, and the data in real time goes to the secondary site and is being loaded on the secondary site. And if disaster happens for the first site, you just enable secondary site. If one of the sites, for instance, secondary site, dies, you still have a replication queue. On these servers, you might make this queue persistent, and you might plan these servers to store up to 3 days, 5 days of data. So when your disaster site will be up again, you would be able to replicate all the data that was not replicated for this time. So you just replaying the events that happened in the past. And this way, you are able to have two platforms in sync. Your time to consume the data is time to insights is getting down to 0. Of course, the bigger your in-memory store is, the faster you would be able to serve the data for the business users. And this is the main idea implemented, for instance, at LinkedIn. They are very proud of implementing this architecture because it allowed them to have a separation of the logic. So you're getting a stream of events from the users. One stream is replicated to a separate queue and replicated to the secondary site. Second stream is replicated and used for analytics on user behavior. Third stream is replicated and used for storing the information itself, like you're pressing the like button, and this goes to the database and like counter increases, and so on and so on. And also this is used at, for instance, Twitter. When Twitter, it's a complex problem, so you might have seen that when you post something in Twitter, the information about this post occurs in all the other users' timeline entries. And the latency is sometimes big. So you're posting something, your friend can sit with you with a phone, and he might see your post in 1 minute, and 2 minutes, it's 3 minutes. But eventually he will see it. The idea is that, first of all, this post gets to the queue. From the queue it gets to the warehouse where they store the post information. And also it goes to the system that updates all the timelines for all the users. It gets all the links, all your friend list, and for all the friends, it executes a separate action of updating their friend list. And this is something like a batch processing. So it allows you to implement very complex architectures. So here is, I shown you one of the examples, how it might look like, and the technologies that might stand behind this implementation. So I'm working at Pivotal, so Pivotal has a number of technologies for working with this. In general, all of these technologies I've shown are open source, so you might use them without licensing, but in general, most of them are supported by Pivotal. So let's start with the Cloud Foundry. Cloud Foundry, I think many of you know, it is the cloud platform, it's infrastructure platform as a service, sorry. Also we got a RabbitMQ, it is a message queuing solution, and Spring platform itself. All the Spring platform is supported by Pivotal and developed by Pivotal. Next is Gemfire and Geode, it is in-memory key value store. Next is Spring XD or Spring Cloud Data Flow. It's again a product for extracting the data in the real time, pipelining this data. It can use inside of Spring Cloud Data Flow. You can use the same RabbitMQ or Kafka as a messaging solution. So it's something like stream processing solution. Also, you can use Hadoop distribution with Hawk. Now it's Apache Hawk, not just Pivotal Hawk. Also, you can use Spark for stream processing the data and for batch processing the data. Basically, Spark streaming processing is micro batches. You can use Postgres as OLTP platform, and Pivotal supports Postgres, but it's up to you. Postgres is an open source, and there are many companies supporting Postgres. And Greenplum, as you might know, 1 month ago, Pivotal also open sourced the Greenplum database, and now it's again an open source MPP solution. So you can easily download it from the GitHub, build it, and use it on your platform. I would say that Greenplum database is good for processing terabytes of data up to 200, 300, 400 terabytes. It can easily process it. Up to 100 servers, it works fine. So here is the data lake idea. You got a transactional database, you offload data to the Hadoop cluster, and you got a reporting database, which is an MPP. Of course, you got many Postgres databases, as I shown you on this big picture. Then you got a Lambda architecture, when from the stream you consume the data through the real-time layer and from the Hadoop layer, and then everything goes to the BI solution. And you got the pipelining architecture, when you got a pipe, and from this pipe of events, you're consuming the data in many different systems and performing different logic on top of them. Some of them might be real-time, some of them might be batch-oriented. So here is the complete solution that you might use. So in general, that's it. If you have any questions, any comments, I would like to answer them.
How can you determine which data goes to Hadoop, which data goes to Spring XD, for example, or to Spring Gemfire?
Yes, it's completely up to you. It depends on what you want to achieve. In Lambda architecture, the idea is that the same data goes to fast data store in memory and batch data store. But it can be completely up to you. It depends on what kind of analysis you need to perform. You might have only real-time graph of some kind of user events, amount of total messages in the same Twitter, amount of messages they receive. It goes only to the real-time layer. You can build similar report on batch, but you might not need it. You want to just monitor what happens on your system. So something like this. It's up to you to define the rules of how this can be routed.
Okay, thank you.
Mm-hmm. Yeah.
Is it possible to have a split brain problem with this architecture? I mean, what if the order of our events coming into our system is matter? For instance, in the gaming world, when you have some large-scale game,
yeah.
if it's delivered in a different order,
mm-hmm.
the data will become inconsistent. So, what is it possible? Is a situation possible when the data between the data master and real-time data is inconsistent?
In general, it's two separate problems. Split brain problem is when you got two masters. If your secondary side will think that it became the new master. The idea is that switch over for the source transactional system to the secondary side should be controlled by someone. Or a different option is to make it automatic, like in many, Facebook, Twitter, and so on. They got a number of data centers. Each data center work mostly with the local customers. So the event happens and they go to the local data center, then gets replicated. If local is not available, it will just go to another one. Eventually, all the events are replicated for all the clusters, and all the clusters has all the information that is important. But you might see that you make a post, and then you can enable VPN, connect to the United States, and see that this post has not happened yet. In the United States, they don't see it. But it happened in your local database, and eventually it will be replicated there. So this is how it works. About the order of events, you got a number of different message queue solutions. Some solutions support ordering, some solutions does not support reordering. So it's up to you to choose the appropriate message queue solution and appropriate settings for it. So that's it in my opinion. Yeah.
Hi. I'm wondering what's the idea behind the Hadoop cluster replication? I'm here.
Yeah. Okay.
Personally, I thought that HDFS already built from scratch with replication in mind, so you could just configure the replication factor. So
Yeah.
what's the idea about replication of Hadoop cluster?
In Hadoop cluster and in general, Google file system is designed to work in a single data center. It works only with low latencies and high bandwidth. If you got one data center in the United States and one data center in Europe, you have no option to replicate the data between them. When the data is written to Hadoop cluster, it is getting pipelined. So you got 3 copies. You write to the first server, it transmits data to the second one, to the third one. When third one acknowledges, it get to the second one, to the first one, and to the customer. So you will not return while you replicate the data. If you will set up a secondary site and it will be far away from the first one, you will always have a huge latency for reading the data. Second problem will be zones. You got Yarn that can define your applications to run anywhere in the cluster. If you will have a single cluster, you might have some mappers run in UK, some mappers run in United States. The problem will be to transfer the data between these mappers when shuffle happens. And there are a number of research on how this can be overcome, but again, nothing yet final. Hadoop will eventually have a replication, but it will be after the version 3.0 somewhere. So it's a very tough problem. You cannot just replicate the data in real time. You should have asynchronous replication.
Yeah, so how would you solve this problem with external replication system? If you want to transfer data from one data center to another.
I have shown you that the best way to transfer the data between 2 data centers is to transfer it before it gets loaded into the Hadoop cluster. So you transfer the real-time stream of events, stream of what happened, transfer it to the remote cluster and get it processed there. Of course, it will require you to have a big processing power, big ETL servers in both data centers. But in general, if you want to replicate all the data from your Hadoop cluster to the secondary side, you should have 2 Hadoop clusters, and these 2 Hadoop clusters should be of the same size. So.
Okay, so basically you should use, for example, Kafka,
yeah.
Yes, just to, but Kafka already too has a replication in their system.
Yes, Kafka has a replication, but replication is not global. You should have a replicated Kafka and redundant Kafka running on your cluster. You consume the event in the queue for this data center, and then you got a separate process that copies data from this queue to a separate queue that is for replication. You got a process that replicates this data to the different data center, and then in this data center it will be consumed. Okay. So the idea is that have a queue, general queue for all the events, and from this queue you are going to the replication queue. This is
great. Thank you.
Okay, thank you for the great talk. It was very interesting. My question is more of curiosity.
Mm-hmm.
So there are 2 bedrocks of Lambda architecture.
Yeah.
Is data immutability,
yes.
and the ability to calculate all your history, aggregate all your history
yeah.
within the batch layer. So
yes.
did you ever happen to do that in Pivotal?
I would say that we got a similar problem with something like 5 years ago with one data warehouse. One of our guys just dropped the data warehouse, and we had to reload all the data from all the source systems. And it taken something like 2 or 3 weeks, and it was it was very bad. So yes, it's really a big problem. This is why Lambda architecture is not yet widely adopted by the end users. You can apply the pattern of Lambda architecture for specific areas of your data. For instance, you got a specific area like clickstream. For clickstream, you can apply Lambda architecture, but for all the other data, you don't apply this. And this is the idea of combining all of these approaches, both Lambda architecture and data lake and pipelining. This is the idea. Yeah.
Hello, thank you for excellent presentation. And my question would be like more architectural. Mm-hmm. So when you place queue between front end and back end, you probably work with application-specific data and respective formats.
Yeah.
And this means that it's not like very generic. So question is, why not you put queue of the database where data format is much more generic, like data log, and can be easily processed in a universal way? So.
One moment, let me come back to the right slide. Yeah. So here you can see that the data. Do I have this working? Yeah. So the data goes to the queue both from CDC after the databases and before the databases. It depends on what kind of data you have, because sometimes from the front end you receive a stream of events, and the only purpose of the backend is to put this event into the database or into the key value store. This way you might avoid putting it to key value store, but at the same time you put it to the different solution.
Yeah,
but if you got some logic inside of the database, some triggers to process the data, yes, you extract the processed data and put it again to the queue for the consumption of all the analytical systems you have.
Okay, thank you.
This is the idea. So, any more questions? So, that's it then. Thank you very much.